Okay, my dear students, class 11 science. Today I shall be bringing the next chapter of the syllabus. Name of the chapter is Classification of Elements and Periodicity in Properties. Now you can see on your screen over there periodic table, a part of the periodic table where it has been mentioned S block elements. Okay. Now, what is periodic table? Periodic table is the table which classifies the elements in such a way that elements having similar properties are grouped together in the same vertical column and dissimilar elements are separated from one another. Now, the main aim of the classification of elements, the main aim of the classification of elements is to make sure that the study is easier. The study of the elements is easier. Okay. Now, as I was talking about the S block elements, S block elements, so much S block elements, the electrons of these S block elements, the outermost electrons enter the S block. S block elements. There. S block over here, I can talk about S block also. For example, if I take beryllium, electronic configuration, atomic number is 4, its electronic configuration is 1s2 2s2. So here the last electrons are entering the S block. Okay, so this one and this one, they come under the S block elements. Okay. Now going slightly in detail, in the next slide, looking at the electronic configuration of S block elements, my dear students, the electronic configuration of S block elements is explained below. The alkali element in S block consists of a single valence electron in the outermost shell. This outermost electron is loosely held, which makes these metals highly electropositive, due to which they are not available in the free state in nature. The electronic configuration of S block elements in group 1 are shown over here. So lithium, its atomic number is 3. So its electronic configuration is 1s2, 2s1. Sodium, 11. Electronic configuration is here. Potassium, 19, and so on. Okay. Now, the electronic configuration of elements included in group 2 of S block elements also given over here. Group 2, which group? Group 2. Like beryllium, magnesium, calcium, strontium, barium, and radium. Okay. So these are the electronic configuration of the elements of group 2. Now properties. Properties of S block elements. Both alkali and alkaline earth metal elements show a regular gradation in their properties among their respective group elements, but the first member of both S block elements, namely lithium and beryllium, differ much from the rest of their members, but at the same time they resemble more than the diagonal element present in the next column. Okay, so looking at the properties over here, the anomaly of this S block element is due to, there is some anomaly, abnormal behavior, characteristics, properties. The S block elements, low atomic and ionic size, greater charge density, greater polarization, absence of d orbitals. Okay, so all these, the anomaly of these S block elements is all this because of all these things: low atomic size, ionic size, greater charge density, greater polarization, absence of d orbitals. Now, when I talk about greater polarization of S block elements, it makes the first element more covalent and differentiates them from the rest, which are ionic. The similarity in the size and charge density makes them resemble the element diagonally placed in the next group, which is called diagonal relationship. It is observed that the physical and chemical properties of these S-block elements change in a particular trend as the atomic number of the element increases. Changes in the various properties of the group are as mentioned below. Okay. Now, regarding the changes, chemical properties of S-block elements, the variation I am talking about. Looking at the atomic and ionic radii, when the S-block elements of the modern periodic table are observed, it is seen that the size of the alkali metals is larger compared to the other elements in a particular period. Particular period. This periods this way. You know. Comparatively, the size of the elements in the first period is larger than the others. Now, as the atomic number increases, the total number of electron increases along with the addition of shells. But on moving down the group, the atomic number increases. As a result, the atomic and ionic radius of the alkali metals also increase because there is an increase in the number of shells. Okay. Now, let us go back to the periodic table very quickly. What is periodic table? That is more important to understand. Now, this periodic table, it is a table of elements in which the elements with similar properties are placed together. A long time back, there was Dobriner who studied the elements and he grouped the elements in triads. So this was the classification of elements into groups of three elements, each with similar properties, such that the atomic weight of the middle element was the arithmetic mean of the other two elements. Example: calcium, strontium, barium. So triad, chlorine, bromine, iodine, another triad. So as you have seen over here, the atomic weight of the middle element was the arithmetic mean of the other two elements. Okay, so here is a very good example. The difference between atomic weights of any two successive elements is nearly constant. Okay. Now come to the Newland law of octaves. Now this was an arrangement of elements in the order of increasing atomic weights, in which it was observed that every eighth element had properties similar to those of the first, just like the eighth note of an octave of a music. Okay. I was talking about diagonal. What is diagonal? The elements of the second period and the third period, resemble themselves with the elements of the third period diagonally placed, like lithium and magnesium, they have similarity in properties. Beryllium and aluminum, similarity in properties. Boron and silicon also, they have similarities in properties. Okay. So these are some information knowledge which you have already learned in classes 10. But here it is done for the sake of revision. Now, after Dobriner came Newland, then there was Mendeleev. Okay. Now, this Mendeleev classification, it is based on Mendeleev's periodic law. It states that the physical and chemical properties of the elements are a periodic function of their atomic weights. Okay. Now, this person Mendeleev named gallium and germanium elements as Ica aluminum and Ica silicon respectively. So that is contribution by Mendeleev. Okay. Then coming to the structural features of the Mendeleev periodic table. This is all history. This is all history. Over here. Point 1. Mendeleev's original periodic table consists of 8 vertical columns called groups 1 to 8 and 7 horizontal rows are called periods 1 to 7. But modified Mendeleev's periodic table contains 9 groups, that is 1 to 8 and 0 of noble gases. All groups except 7 and 0 have been further divided into two subgroups called A and B. A group of left-hand side consists of normal elements while B consists of transition elements. Elements of group 1A are called alkali metals while those of group 1B they are called coinage metals like copper, silver, gold and coinage metals. Okay. After this came the development from the contribution of Mosley. Then that is why we have the modern periodic law. The Mosley he formed the basis of the modern periodic law. This fellow he discovered that the square root of the frequency of the more prominent X-rays emitted by a metal was proportional to the atomic number and not the atomic weight. So here atomic number plays a very important role. A very important role in this law. Now, hence, according to this modern periodic law, stating that the physical and chemical properties of the elements, are a periodic function of their atomic numbers. Okay. Now it was observed that the elements with similar properties reoccurred at regular intervals of either 18 or 32. These numbers are called magic numbers and cause periodicity in properties. Recurrence, the word reoccurrence, it is very important over here. Okay. Now, quickly going to the structural features of the long form of the periodic table. Groups. First, the groups. The 18 vertical columns of the periodic table are called groups. The groups this way. If you look at this way, they are the groups. Now, the elements of group 1, 2, 13, 17 are called normal or representative elements. Okay. Remember 1, 2, 13 to 17. They are called normal or representative elements because they are very true to their electronic configuration. Whereas, my dear students, the elements of group 3 to 12 are called transition elements. Number 4, the elements belonging to a particular group is known as a family and is usually named after the first element. For example, if you talk about this boron family, group 13, In addition to this, some groups have typical names. Alkali metals. Group 1 elements are called alkali metals. Why alkali metals? Because when these elements react with water, they form strong alkali solutions. Similarly, group 2 elements are called alkaline earth metals because these elements they also react with water to produce basic solutions. Group 2 elements they are called nicogens, then group 16 chalcogens, 17 they are called halogens, 18 are called noble gases. So I will suggest you all to remember these nicknames of these groups 1, 2, 3, 16, 17, 18 and so on. Then talking about the periods very quickly. You know what are periods? The 7 horizontal columns or rows are called periods. The 7 periods of periodic table are first, second and third periods which are called short periods containing 2, 8 and 8 elements. Okay. Fourth, fifth and sixth periods contain 18, 18, 32 elements which are long periods. And the seventh period is incomplete. It is not complete, incomplete. And it may contain, total 32 elements. Addition can still happen over there in the 7th period, for the newly discovered elements. Now, my dear students, coming to the blocks, block. The periodic table is divided into 4 main blocks, that is S block, P block, D block and F block depending upon the subshell to which the valence electron enters. Remember, for the S block elements of group 1 and 2 constitute the S block. Remember this. For the P block elements of group from 13 to 18 constitute the P block. Okay. Number 3, D block. Elements of group 3 to 12 constitute the D block. Okay. Now, for this, let me give you some idea over here. Okay, come to the come to over here. Okay, so I have told you this is the S block. Then here, you know, P block will be here. This will be the P block. This much will be the P block, and this is the D block. D block. This will be the P block. Okay, and S block. I already told you this also comes into S block. This also comes into S block. Okay. Now, now coming back to our required slide. Now, number 4. There are 3 complete series and 1 incomplete series of D block elements. Okay. The first and the 3D transition series contains 10 elements with atomic number 21 to 30, like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, that way. Then second or 4D transition series, 39 to 48, yttrium to cadmium. Third or 5D transition series which also contain 10 elements with atomic number 57 and 72 to 80, starting from lanthanum to hydronium, mercury. Fourth or 6D transition series which contains only 10 elements. Okay, so the first or 3D transition series elements, the first or 3D transition series, this I would like you all to remember, learn this series possibly by heart, like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Atomic number 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Okay, so I would like you all to remember this by heart, by heart. Then moving to the F block. The F block elements comprise 2 horizontal rows placed at the bottom of the periodic table to avoid its unnecessary expansion and make the symmetrical nature of the periodic table. The 2 series of F block elements containing 14 elements each. Lanthanides, the 14 elements from 58 cerium to lutetium in which 4F subshell is being progressively filled up are called lanthanides or rare earth elements. Actinides, similarly, the 14 elements from 90 thorium to 103 Lr in which the 5F subshell is being progressively filled up are called actinides. Number 6. Elements of S and P block are called normal representative elements. I have told you at that time already. Those of D block are called transition elements, while the F block elements are called inner transition elements. Okay. The 11 elements of with Z93 to 103 which occur in the periodic table after uranium and have been prepared by artificial means are called transuranics. Transuranics are radioactive elements. Okay, that is wonderful. Now, going to the nomenclature, nomenclature of elements with atomic number greater than 100, say 101, 102, 103, over here, there is some set of rules mentioned over here. According to the International Union of Pure and Applied Chemistry, the nomenclature can be derived using numerical roots for 0 and numbers 1 to 9 for atomic numbers of elements. Now, the roots are put together in order of digits which make the atomic number and EM is added at them. IUM, okay, IUM. This is nothing but it is IUM. Okay, use the following table. Just let's do an example. That if digit is 0, we give it a name nil. Abbreviation is N, 1 is un, U, by, B, 3 is try, T, 4 is quad, Q, 5 is spent, P, 6 is hex, H, 7 is sept, S, 8 is oct, O, 9 is Ne. So these are the abbreviations for the various atomic numbers. Let's do an example. For example, there is a question. Name the IUPAC. The IUPAC name of the element with atomic number 108. 1 is what? UN. UN. Okay. 0 is what? Nil. So NIL nil. 1 is what over here? 1. It is UN. UN. 1. No. The next is 0. 8. No. So 0 is what? Nil. UN. NIL. Okay. Then 8. It is oct. Look at this. It is oct. So OCT. Oct. Then at the end you put IUM. Wonderfully. IUM. Okay. IUM. That is how you name according to the IPC for atomic number of elements greater than 100. You can take another example also over here with atomic number 115. 115. The one is again N. Un. Another one is there. So another un. Then there is 5. There is 5. So for 5 you see pent. Pent. I write pent. Pent. Then at the end put IUM. IUM. So for element with atomic number 115, the IPC name is pentium. So take elements with atomic numbers from 101 to 120 and try naming yourself near of exercise copies. You will just enjoy this. It is wonderful. It is just marvelous. Okay. Now let's look at this topic over here, diagonal relationship. Now here, my dear students, please keep in mind certain elements of second period, example lithium, beryllium, boron, they show similarity with their diagonal elements in the third period. Those are magnesium, aluminum, silicon. Here it is shown in this diagram over here. Okay. So this relationship, it is called diagonal relationship, and is due to the reason that this pair of elements have almost identical ionic radii. A very important point to be noted. This relationship, diagonal relationship, is because of almost identical ionic radii and polarizing power. Now polarizing power, remember, charge. It is charge by size ratio, radius ratio. Okay. Now let us move to the properties, periodic properties, the main topic in this chapter, periodicity properties. Now, properties which show a regular gradation, increase or decrease, when we move from left to right in a period or from top to bottom in a group are called periodic properties, which is a known fact by you all. Now these properties are atomic size, first one, ionization energy, electron affinity, electronegativity, metallic, non-metallic character, and so on. Okay, we'll discuss them slowly. Now, the first periodic property is atomic size. Now, when I talk about atomic size, my dear students, it refers to the distance between the center of the nucleus of an atom to its outermost shell of electrons. The absolute value of atomic radius cannot be determined because it is not possible to locate the exact position of the electron in an atom, as an orbital has no sharp boundaries. It is not possible to isolate an individual atom as well. In a group of atoms, the probability distribution of electron is influenced by the presence of neighboring atoms. Since absolute value of atomic size cannot be determined, it is expressed in terms of the operational definitions such as covalent radius, Van der Waals radius, Ionic radius, and so on. Looking at atomic size, get hold of covalent radius. Now you can see the formula over here. The covalent radius is half of d. Now this d means internuclear distance between the two covalently bonded like atoms. Okay, so this covalent radius can also be attributed to the atomic size, which is the first periodic property in this chapter. Now, after the covalent radius, we can talk about the Van der Waals radius also. Now, this Van der Waals radius, it is 1/2 of the distance between the nuclei of two adjacent atoms belonging to two neighboring molecules of an element in the solid state. The covalent radius is always smaller than the corresponding van der Waals radius. Okay. Now we come to the metallic radius. It is half of the distance between two successive nuclei of two adjacent metal atoms. Metal atoms, remember, in the metallic closed packed crystal lattice. Metallic radius of an element is always greater than its covalent radius. Important fact to remember. Okay, please keep in mind, my dear guys, over here, metallic radius of an element is always greater than its covalent radius. Then moving to the ionic radius. The ionic radius, it is the effective distance from the nucleus of an ion. So when I talk about ions, up to the electron in the outermost shell to which it can influence the ionic bond. An atom can be changed into a cation by loss of electron. That is a fact which is known by all of us since class 8, which is always much smaller than the corresponding atom, or to an anion, which is formed by the gaining of electron, which is always larger than the corresponding atom. Now, coming to the factors influencing covalent radius. Number one, the first factor, first factor is covalent rate depends on the multiplicity of bonds. When I say multiplicity of bonds, carbon-carbon single bond is possible, carbon-carbon double bond is possible, carbon-carbon triple bond is possible. So as the number of bonds between two atoms increases, the covalent radius also decreases, inverse proportionality. Now, the second factor is percentage of ionic character. Covalent radius of hydrogen in HBr, HCl and Hi are different. Remember that. So this you can talk about, the covalent radius of H. It is different. Why? Why? Because of the ionic character. Ionic character. If you move from chlorine, bromine, iodine, the size of the halogen atom, it is increasing. That is why the percentage of ionic character is also varying over here. Then moving to number 3, the effective nuclear charge. Greater the effective nuclear charge, more tightly it will be held the nucleus, and hence smaller will be the radius. Keep that in mind. These are some factors which are going to influence the covalent radius in this chapter. Then, my dear students, coming to the main topic over here, variation, periodic variation of all these properties. The first one is atomic radii. On moving down the group, the valence shell becomes far away from the nucleus and thus the atomic radius decreases. On the other hand, on moving along the period, the effective nuclear charge increases and thus the electron cloud is attracted more strongly toward the nucleus, resulting in the contraction of the atomic radius. Now, coming to one word over here, isoelectronic ions or species. These are ions of the different elements which have the same number of electrons but different magnitude of the nuclear charge. The size of isoelectronic ions decreases with the increase in the nuclear charge. Okay, so the first periodic property I briefly discussed. Okay, so to enhance your knowledge, you may refer to our textbook, and get some knowledge on this atomic size variation. Okay, coming to the next periodic property, which is ionization energy. Now, definition of ionization energy: the amount of energy work required to remove an electron from the last orbit of an isolated free atom in gaseous state is known as ionization energy or potential energy, or better, first ionization energy of the element. Okay, now here let me tell you something. The amount of energy required to remove the subsequent electrons, first, second, or third, they are categorized as successive ionization energies. These are designated as I1, I2, I3 and so on. Okay. It may be noted that I4 is greater than I3, greater than I2 and I1 is least for a particular element. Okay. Then In general, the first I increases along the period from left to right. However, there are some exceptions to the general trend. Ionization decreases from elements of group 2 to 3. Decrease in ionization energy. Ionization energy decreases from elements of group 15 to 16. Okay. In the group of periodic table, the ionization energy decreases from top to bottom. We move from top to bottom because of the increasing atomic size. It is much easier to remove electrons from the valence shell. That is why it is decreasing over here. Okay. Now, coming to the atomic size or radius. Ionization energy decreases as the atomic size increases, so the attractive force decreases. Love this. Number of electrons in the inner shell. If there are number of electrons in the inner shell, it is going to cause some screening effect. On moving down a group, the number of inner shell increases, which increases the screening effect, and hence the ionization potential tends to decrease. Keep that in mind. So when you're moving down the group, my dear boys, there are number of electrons in the inner orbitals, inner shells, and that is going to block the effect of the nucleus on the valence shell electrons. So what is going to happen? The ionization energy will decrease. Wonderful point over here. The number 3, nuclear charge. On moving along the period, effective nuclear charge increases due to addition of electrons in the same valence shell, and hence ionization energy also increases. Then number 4, stable configuration. Very important point over here. Half-filled or incompletely filled subshells possess extra stable nature, and thus it is more difficult to remove electron, and hence more is the ionization energy. So keep this in mind. Half-filled or completely filled subshells, possess extra stability. For example, if I have a d orbital, d orbital 1, 2, 3, 4 and 5, and this d orbital has 1, 2, 3, 4, 5 electrons, 1 electrons each in the orbitals. Okay. Now if you look at this, this is what? This is a d orbital which is half filled. Okay. If I have the same d orbital like this, 1, 2, 3, 4 electrons. This is also a d orbital, but this is incompletely filled. So this will have lesser stability than the previous one. So keep in mind, half filled or completely filled orbitals, they possess extra stability. Okay. Then coming to the penetration effect, more penetrating, that is more closest, more penetrating are subshells of a cell to the nucleus. More tightly the electrons are held towards the nucleus, and more is the ionization energy. Okay, so remember, s orbitals are closer to the nucleus, p are far away, then rd, then f. So because of the s orbitals are closer to the nucleus, the electrons of the s orbitals, they are more penetrating. They penetrate the orbitals of the inner orbital subshells. That's why that is going to cause penetration effect. Okay. Remember, penetration power is directly proportional to the surface area of a subshell. Okay, so learn this point properly. More penetrating are subshells of a shell to the nucleus, more tightly the electrons held towards the nucleus, and more is ionization energy. That means electrons of s orbitals are more penetrating, and second most penetrating, then third most penetrating, and fourth most penetrating. That means you will find the electrons in the s orbitals are more closer towards the nucleus. Okay, that is why it becomes very difficult for guys like us to remove electrons from the s orbitals because of the penetration effect. Okay, so this has been discussed over here. Number 5. In second period elements, the correct increasing order of ionization energy is given over here. Try to remember this. Okay, the order. lithium, beryllium, boron, beryllium, carbon, oxygen, nitrogen, fluorine, neon. The second ionization is boron, carbon, boron, beryllium, carbon, boron, nitrogen, fluorine, oxygen, neon, and lithium. Similarly, this has been done over here also. Now, my dear students, looking at the electron affinity, as per the definition, it is the amount of energy released when a gaseous atom accepts the electron to form a gaseous anion. A gaseous atom is accepting what? The electron to form a gaseous anion. Okay. The energy released, electron affinity is the energy released when a gaseous atom is accepting the electron to form a gaseous anion. Okay. I hope my my IIT JEE aspirant is watching this video very carefully. Okay. Number one, the electron affinity values are expressed in electron volt atom or kilocalories per mole or kilojoules per mole. The energy change accompanying the addition of first, second, third, etc. electrons to neutral isolated gaseous atoms are called successive electron affinities and are designated as EA1, EA2, EA3, etc. etc. The first important point, very important point over here. The first electron affinity is always taken as positive. However, the addition of second electron to the negatively charged ion is opposed by Coulombic repulsion and hence required absorbed energy for the addition of second electron. Thus, second electron affinity of an element is taken as negative. Example is here. Oxygen, if you add electron, becomes O minus. Okay. Now, since this is O minus, it will create Coulombic repulsion to the incoming electron. EA1 is positive, but EA2 will have a negative value of the electron affinity. Okay. Then, my dear students, moving to next slide over here. Electron affinity increases in moving along the period from left to right due to increase in charge, effective nuclear charge. But the values are unexpectedly low in elements of group 2, 15 and 18 due to stable electronic configuration of exactly half-filled and completely filled orbitals. Very important point to remember. I have told you half-filled and completely filled orbitals, they have extra stability. That is why these values of electron affinity are unexpectedly low in elements of these groups 2, 15, 18. Okay. Now, within a group of the periodic table, the electron affinity decreases from top to bottom. In general, electron affinity follows the following trend. Halogens, highest electron affinity, then oxygen family, then nitrogen family, metals of group 1 to 13, and non-metals of group 14, and so on. The electron affinity are indirectly measured with the help of a cycle, bond-Haber cycle. Okay. Delta HF, enthalpy S, IER is given, heat of sublimation, bond dissociation energy, ionization energy, electron affinity, and this one is lattice energy respectively. Okay, so I hope you got the idea. Sublimation, bond dissociation energy, ionization enthalpy, electron affinity, and lattice energy. That gives us the enthalpy of formation. Okay, so this can be, the electron affinities can be indirectly measured in this manner. Now, moving on upon to the dependence, of electron affinity. Electron affinity, my dear boys, depends upon effective nuclear charge. Greater the effective nuclear charge, more is the attraction of the nucleus towards the electron, and hence higher will be the value of electron affinity. Atomic size. The second thing is atomic size. Greater the atomic radius of the atom, less will be the attraction of the nucleus to the electron to be added, and hence lower will be the value of electron affinity. Penetrating power. Now, due to the penetrating power, Electronegativity for addition of electrons show the order S greater than P greater than D greater than F. Okay, so addition of electrons in s orbitals, is highest because of the penetrating power. Then electronic configuration. I have been telling again and again. Half-filled and fully filled subshell are extra stable and thus oppose the addition of electron, which leads to lower EA value. Okay, carbon greater than electron affinity than nitrogen. Okay, that was electron affinity. Coming to the electronegativity En over here. Now, electronegativity, my dear students, it is the tendency of an atom in a molecule to attract the bonded shape pair of electrons to itself. So, now this electronegativity has been measured on various scales. One is Mulliken scale, the other one is Pauling scale. Remember these names, and if possible, try to remember this formula also. Okay. So, on the Mulliken scale, there is a formula to measure the electronegativity represented by capital X. IE plus EA divided by 2, where IE is ionization energy and electronegativity expressed in electron volts. On the Pauling scale, this is the most widely used scale nowadays and is based upon bond energy data. Bond energy data is there. According to the Pauling scale, the difference in electronegativity of two atoms A and B is given by a relationship XA minus XB 0.208 under root delta E, bond energy data in SI units. Okay, so 0.088 delta E, that will be sufficient. Okay, then the electronegativity in a period increases from left to right due to decrease in size and increase in nuclear charge of the atoms. In a group, electronegativity decreases from top to bottom due to increase in atomic size. Okay, remember this properly. Now, electronegativity depends upon atomic size, nuclear charge, shielding effect. Shielding, the electrons, present in the inner orbital, they shield the effect of the nucleus on the outermost shells. Then oxidation state. Electronegativity increases as the positive oxidation state increases. That means plus 2, plus 4. This is increasing. So, with the increase of this, the electronegativity also increases. Hybridization. This is a very, very important thing over here. Greater the S character in a hybrid orbital, more is the electronegativity. That means SP, 50%, 50%. SP2, this is S character is less. SP3, S character is much less. That means SP orbitals, SP orbitals, elements having SP orbitals, they will have greater, electronegativity. Okay, over here. Then, if electronegativity difference is greater than 1.7, remember this figure 1.7. If the electronegativity difference is greater than 1.7, the bond is ionic. Otherwise, it will be covalent. Very, very important point. In general, greater is difference of electron between two atoms, smaller is the bond length. So, if the difference of the electronegativity is greater, the length of the bond is smaller. Okay. When smaller is the electronegativity, larger is the atomic size, my dear students. Okay. Then moving to the valency. Valency of an element is the number of electrons gained or lost or shared with the other atoms in the formation of compounds. Okay, number of electrons which are gained, lost or shared. So that comes under valency. Valency of group 1 and 2 elements is equal to the number of electrons in the outermost shell, while that for groups 13 to 14 is group number minus 10, and that for group 15 to 18 is 8 minus the number of electrons in the outermost shell. That is how to get the valency, which we have been doing since class 10. Okay. Now, atomic volume. This is one word we will be coming across this full year in class 11 as well as in class 12. Now, it may be defined. This atomic volume is defined as the volume occupied by one mole atom of the element at its melting point in solid state. It is obtained by dividing the gram atomic mass of the element by its density. Okay. The atomic volume decreases along the period. becomes smaller in size, reaches a minimum in the middle, and then starts increasing because of different packing arrangement of the atom in different elements in the solid state. Like for example, P4 tetraatomic, S8 octatomic. Okay. In moving down the group, atomic volume goes on increasing gradually. Okay. Then coming to the acid base behavior of oxides and hydroxides in this chapter. Okay. This you can go through, and this is a very important slide over here for you all to go through, try to memorize, try to understand. When I talk about the oxides or hydroxides of an element, they may either be act as a base or an acid depending upon its ionization energy. Metallic oxides, metallic oxides are basic in nature, alkaline, and non-metallic oxides are acidic in nature. If the ionization energy is low, it is going to act as a base. Please learn this properly. And if the ionization energy is high, it is acting as an acid. See, wonderful thing over here. A very brand new thing to be understood by all of you. The ionization energy of alkali metals is the lowest. Therefore, their oxides and hydroxides are the strongest bases. The basic character of the hydroxide increases in this order. Okay. Then number 3, the ionization energy of halogens is quite high. Therefore, their oxides are the strongest acids. The acidic character of their oxides and hydroxides decreases in this order. That is the halogens. Oxides are the strongest acids. See, it's an acid per chloric acid, per bromic acid, per iodic acid. Okay. So this is the order of decreasing order. Strongest is this one. Second strongest, weakest acid. Within a period, the ionization energy of the elements usually increase, and hence, my dear students, the oxides and hydroxides show a gradual variation from strongly basic through amphoteric to strongly acidic character. Then number 5, the non-metallic character, oxidizing character, and acidic nature of the oxide of the element increases from left to right in a period and decreases from top to bottom in a group. Non-metallic character is what? Increasing. Oxidizing character is what? Increasing. Acidic nature of oxide is also increasing from left to right. And then, but if you move from top to bottom in a group, it is going to decrease. The stability of the metal increases and activity decreases from, activity means reactivity, from left to right in a period, whereas the stability decreases and activity increases down the group. Now, my dear students, I have just started this chapter, classification of elements and periodicity and properties. Now in my next video, I shall be discussing this chapter in detail, coming across various question answers, reason based question answers, and the question patterns, the type of questions that is normally asked from this chapter. So I would like to end my video over here. Okay, please go through this introduction chapter, classification of elements and periodicity properties very carefully. Okay, so meet you in my next video. Thank you so much.